So now you got the static margin field, but can you notice one more thing here? Cm naught you have found out for the total aircraft, Cm alpha you have found out, but when you place the tail, the total CL naught of the wing will be different from the CL naught coming wing alone, and CL alpha also will be the different. Okay, so now we can find out the total CL naught and total CL alpha, which is the coming from wing and after placing the tail. Total lift equal to lift of wing plus lift of tail. Total lift you can write half rho v square s into CL, and wing lift you can write half rho v square s into CL of the wing, and tail lift you can write half rho Vt square tail area into CL of the tail, and you non-dimensionalize this by dividing the half rho V square S. So at left hand side you will be having CL, and at the right hand side you will have CLW, and plus eta. Eta is coming the ratio of half rho Vt square dynamic pressure at the tail and dynamic pressure of the wing. Okay, so eta, and then St by S is appearing here. Okay, that you can write, and CL alpha of the tail you can write, because CL you can write CL alpha of the tail into alpha of the tail. Since symmetrical airfoil we have chosen for a tail, so CL naught of the tail will be 0. Okay, we know what is alpha tail, alpha W minus IW minus epsilon naught plus IT. You further break the epsilon naught as epsilon naught plus dou epsilon by dou alpha into alpha by the Taylor series, and consider only first order and neglect higher order terms. Okay, and then you can write CL as a CL naught plus CL alpha into alpha, and then compare CL naught terms from the left and right hand side, and similarly for the CL alpha you will get CL naught will be the CL alpha of the wing plus eta St by S IT minus IW minus epsilon naught, and total CL alpha of the aircraft will be the CL alpha of the wing plus eta St by S1 minus dou epsilon by dou alpha. So you can see that this is a extra part, this is a extra part is coming by placing the tail. Okay, and this is also extra part coming by placing the tail. Okay, now we have CL naught, CL alpha, CM naught, CM alpha. Okay, CL that means force, lift force, CM means pitching moment. So one force equation, one moment equation in non-dimensional manner we can write CL equal to CL naught plus CL alpha into alpha plus CL delta into delta E, and CM equal to CM naught plus CM alpha into alpha plus CM delta into delta E. Now please note that we have added extra term CL delta E and CM delta E, and here delta E and here. So what is this? So you can look into this aircraft. This is an elevator. If you deflect the elevator, the CL will change, right? So this part is nothing but the control part. You can write pitching moment due to elevator and force, lift force due to elevator. Okay, you can write. Now when you are having CL equal to CL naught plus CL alpha into alpha and CM equal to CM naught plus CM alpha into alpha, okay, if you deflect the elevator, your lift will change, right? Because only due to elevator deflection the lift is changing, and lift is changing where? Lift is changing at the tail. So you can write change in lift equal to change in lift at tail. Now further same thing for a non-dimensional, you divide by half rho square S and you will end to see the delta CL will be the eta St by S delta CL alpha of the tail. Okay, you can divide by this delta E because I want to find CL delta E. CL delta E, that means CL dou CL by dou delta E is a CL delta E only, right? So if you change the elevator, how the CL is changing, that is nothing but this CL delta E. Okay. It will give the sensitivity of the elevator. If you deflect the elevator, how fast you are and how slow you are changing the CL. Okay. So you divide by delta E, and here you can write CL delta E eta st by s dou CL by t into delta E, and further you can write as a dou CL by dou alpha t and dou alpha t by dou delta E, and this you call dou alpha by delta t as a tau. Okay, and you can finally write CL delta equal to eta tau st by s CL alpha of a tail. So tau, what is tau? Tau, for example, like if you can find out using this graph, this is a elevator area, control surface area by the lifting area, horizontal area you can say. Okay, lifting area is horizontal area, total lifting area, and delta is a control surface area. So you can mark as a 0.1, 0.2, 0.3, 0.4, 0.5, and here say 0.1, 0.2, 0.3, 0.4, 0.5. So roughly you will have this kind of graph where you can, based on the control surface area by lifting area, you can find out the value of tau. Similarly, when you deflect the elevator, there will be change in CM. So delta CM, you can write delta CM in change at tail. So further you non-dimensional things, you will get CM delta equal to minus eta Vs tau CL alpha of the tail. So here, while 9-dimensionalizing, you multiply half rho v square s into c. In the last case, we have divided by the half rho v square s because that was the force and this is a moment. Okay, and this is moment arm is coming here. So st lt s into c bar will be vh, and rest of the terms will remain the same. So now we have a one complete force equation and one complete moment equation, and let's say if you want to fly the aircraft in a steady state level flight, now we have a one lift force and one moment force, and if you want to fly at a steady state level flight, then you have to use the controls in a such a manner you should not get any net pitching moment. That means Cm is 0 and whatever angle of attack you are flying, that is a trim angle of attack. Okay, this alpha is a trim angle of attack, and whatever CL you are flying corresponding to this angle of attack will be the CL trim. Okay, so this is a two equation and two unknowns sitting here, one is alpha and one is delta E. So you can take Cm naught at this side and CL trim at this side, make a one matrix here, and what are the coefficient associated with alpha? Cm alpha, and here Cm delta E, and here is CL alpha, and here is CL delta E. You can have one matrix 2 cross 2 A matrix, and this is the unknown you denote as a X, which is alpha trim and delta E trim. Okay, and the solution of this equation will give you the alpha trim and delta E trim. So now we have a delta E trim and alpha trim. You can plot this with respect to the velocity. You can take a scale of velocity as a starting from stall and 2 times or 3 times v stall, and at each velocity you will calculate the CL using this lift equal to weight equation 2W divided by rho square S. You are particularly flying at one particular altitude, so rho is constant. You have sized the aircraft, S is constant. Put the different value of V, you will get the different value of CL. If you get the different value of CL, you will get the different value of alpha. Okay, in order to attain that alpha, you will get the different value of delta. So the graphs will look like this. As long as you increase the velocity, your alpha will go down, okay, and if you increase the velocity, your delta item will look like this. Here the delta is negative sign and here is positive sign. You can have some feel for also. For example, if you are uh, uh, flying with a low velocity, you have to deflect the elevator up, and up is negative, you can see here. And if you are flying very high velocity, okay, that means you have to deflect the elevator down to reduce the angle of attack, and down is considered as a positive, so you can see the positive deflection. Okay, this is all about the aircraft longitudinal stability and control. Thank you very much for it.